All right, let's try this baseball diamond problem from the related rate section. So hopefully we can get through it. I'm not sure if everybody's actually played baseball. Um, I know I've got a few childhood nightmares from baseball, but let's see if we can get through this. Okay, so a baseball diamond is a square with sides of length 90 feet. So let's go ahead and just set up our baseball diamond here, and let's see if we agree with uh, what we're doing here, the setup anyway. And so this is, I'm thinking of as home plate, right? And so, does everybody know first base is over here, right? First base, and then second base, and then third base, and then back to home. Okay, so the pitcher's over here somewhere. Good. All right, so we're told that a baseball diamond's a square with 90 feet on each side, so these are each 90, right? And a player is going from second to third at 24 feet per second. So let's go ahead and just put our player in here somewhere. So there's our player, and they're moving right towards third. Okay, let theta be the angle between the third baseline. This is what's the third baseline? This is the third baseline. And the line of sight from the umpire to the runner. So the umpire is standing, let's say he's standing on home plate just to make sure our drawing is accurate. And then this would be our line of sight, right, from the umpire to the player. Good. And so theta then would be the angle between. Okay. And so it looks like this is going to be our right triangle then, huh? And so we know that the length of this side is going to be 90. What do we want to find out? How fast is theta changing when the runner is 30 feet from third base? So let's let x be the distance the runner is from third base. Okay. And now we could put a variable in here for the length from home plate to the runner, but so far we haven't needed that. So let's leave that as a let's leave that until we actually need it. So what is the relationship between these variables then? Well, if we just use x and 90, right, that would be opposite over adjacent, and so that would be the tangent of theta. So let's go ahead and take tangent of theta, and in fact theta is a function of t, right, is equal to x of t over 90. Remember, the 90 is fixed, but x of t is not fixed, right? Good. What's some other things we know here? The player is going from second to third at 24 feet per second, so we know that dx over dt is equal to 24. What else do we know? Let's see. So how fast is theta? So we want to find d theta over dt when x equals 30, right? And dx over dt is 24. Good. I think we can do that. So before we put in x equals 30, right, you want to treat x and theta as functions of time when you're taking the derivative. So we'll just differentiate this directly. You can put the 90 over here if you want. So let's go ahead and do that. Well, I guess we don't need to. So derivative of tangent is secant squared. And so that's theta of t stays in there times our d theta over dt. And so that would be like 1 over 90 times x of t. So 1 over 90 times dx over dt. Good. And now, I guess I didn't really use the fact that x was 30, except, you know, in this triangle, when x is 30, my triangle looks like this, right? And so what's the secant of that triangle going to be? So the secant is going to be 1 over the cosine. I think we did this in the last problem too. So I'm going to need to know what this distance is. Okay, so that's going to be the square root of 90 squared plus 30 squared. Good. Let me pause while I compute that real quick. Alright, so computing our hypotenuse, it was the square root of 90 squared plus 30 squared, which is the square root of 9,000. And so you could leave it as that, or you could rewrite it as this approximately 94.87. Okay, so we will plug that in. That's going to be the 90. What's going to be the secant squared? Secant is hypotenuse divided by adjacent. Okay, I'm going to run out of space down here. Okay, so my I'm computing the secant squared of theta now, which is the 94.87 divided by 90 squared times d theta over dt is equal to 1 over 90 times dx over dt. Okay, and we want d theta over dt. Let's see, what's 94 over 87, or 94.87 divided by 90 squared. 1.11 times d theta over dt is equal to 1 over 90. Now dx over dt. You know, in this last page here I said that dx over dt was 24, but I have to be careful here. This is the speed, right? The speed of the player. But notice that x is getting smaller and smaller. So actually I should be writing dx over dt as a negative sign, with a negative sign there. So let's go ahead and put a negative sign in. And again, the negative sign is because x is getting smaller and not bigger, right? So that's the difference between speed and velocity. So let's go ahead and put in negative 24 for our dx over dt here. 1 over 90 times minus 24. Good. Now it's all over except the computation. Let's see, put a negative sign, so that's going to be minus 0.2667 or so. Okay. And so we get that d theta over dt is approximately minus 0.24 radians per second. Good. Now why is the theta also negative, d theta over dt? So notice that as x gets smaller, our theta also gets smaller. And so that's why you can kind of check yourself that the sign of the derivative is correct. Good, there we go. So this is the rate of change of the angle between the umpire and the third baseline when the runner was 30 feet from third base. Good. All right, I think we have, we'll try to do one more.